In this video, I'm going to be looking at a thing called the equilibrium constant. It's really just our introduction to equilibrium. And I'm going to use the 2013 NCEA paper about reactivity, chemical reactivity, to go through some actual examples of this, including some stuff we've already learned about equilibrium in our previous lessons. So what we've got here is a generic equilibrium reaction where A moles of A plus B moles of B are in equilibrium with C moles of C and D moles of chemical D. The way that we turn this into an equilibrium constant or equilibrium expression is, as you see there with the Kc, so K is the equilibrium constant, C just means constant really. There are different types of K expressions and you'll meet those next year. So we go the products to the power of how many moles there are over the reactants to the power of how many moles of those are in a balanced equation. The square brackets actually mean the concentration, so they mean moles per litre or moles per decimetre cubed, depending on what you normally use. We're using moles per litre this year. They mean exactly the same thing. One of the things you'll notice is that it's products over reactants. So if the K value is really big, then that means that there's a lot more reactants than there are products. So even though we call it an equilibrium, it doesn't mean there's equal amounts of each thing. For that to be the case, then the answer for K would be 1. Conversely, if there's a very small K value, it means that not much has been turned into the reactants. So you've got a lot more product. If K is very small, then it means that not a lot of the reactants have turned into products. So you've got a higher concentration of reactants than products. One of the other things that's really useful about K values is that if we change one of the conditions and let Le Chatelier's principle come into play, then we're going to see the effect of changing that condition by how the K value changes, getting bigger or smaller. So if Kc gets bigger, it means that the forward reaction must have been favoured because the concentration of the reactants has gone up. So if I was, for example, to heat the system up, so I'm sorry, I've only said if that changes temperature. If that changes an increased temperature, you would infer that the endothermic reaction is favoured, so that would be the forward one. That's because, using the Chatelier's principle, if I'm going to heat a system up, it's going to shift in the direction that will try to absorb some of that heat energy. So K would get bigger if this was an endothermic reaction if I increase temperature. We'll see why that's important shortly when we go through some of these examples. So one of the key things that we have to be able to do is to be able to write a K expression or use a K expression to write an equilibrium equation. So that's going to be our first question. So you can see where I've got this information from, the 2013 NCEA exam paper. So the first thing we see here is that we've got our reaction here, and sorry, I'm just going to tidy up these text boxes a little bit. Okay, it's products over reactants, and I use square brackets. So I've got NH3 gas. I'm sorry, I'm not going to use the subscripts in this video just for simplicity. So NH3 is going to be on the top, and see the 2 in front of it? This means that that number has to be squared. So I put the 2 as a squared. On the bottom, I'm going to have nitrogen and hydrogen. So again, in square brackets, I'll put my nitrogen, and that will be multiplied by, but being maths, I don't need to say that. This is implied. So the concentration of nitrogen times the concentration of hydrogen. And if I have a look at the the hydrogen, it's got a 3 in front of it. Pardon me. So I have to cube that value. So this would be my equilibrium expression for this reaction here, the Haber process. Just like that, I've got to be able to take an expression and pull it apart. So if I see here, SO3 gas is on the right hand is on the top, so it's my products. So I put SO3, and I probably should put my gas there as well. The reason that we care about the gas, that we worry about gas is if we were to change pressure, for example. And on the on the left hand side, I'm going to have SO2 gas reacting with oxygen gas. Now I haven't quite finished here, so don't think I've forgotten what to do. The little squareds here are going to be the number of moles of things. So I need to still put a 2 in front of this because of the 2 here. And I still need to put a 2 in front of SO2 because of the 2 here. So that's one of our first skills, is being able to write an equilibrium expression there, and then conversely turn an equilibrium expression into a balanced equation. Right, let's see our next thing that we're being asked to do in this question. The next one it's asking us to look at is the effect of changing conditions. Okay, and this is pressure, as it says there. So pressure, an increase in pressure will only affect systems that have got gases in them, and these two systems do. It will actually only have an effect if there is a difference in the number of moles of gases on each side. So I'm going to state what pressure would do. So an increase in pressure favours the reaction that produces fewer gas molecules. It only has an effect upon system or equilibria which have gas molecules in them. Okay, it says compare and contrast. So compare, I'm going to say that I'm going to do the comparison first. Both of these reactions involve gases, so may be affected by a change in pressure. However, reaction 1, I've used that word, so why don't I do it, has 2 moles of reactants, 2 moles of reactants, which are gases, and 2 moles of products, which are gases. Now, what I'm going to put in there as well, I know you can do this if you're handwriting, but I'm also going to put in there what they were. 1 mole H2. Sorry, a bit of a formatting issue there, we'll fix that. One mole N2. And again with the products, might as well say what it is. So 2 moles of HI. Therefore, change in pressure has no effect. Reaction 2, on the other hand, has 4 moles of gases sorry, 4 moles of reagents, which are gases, reactants. So my mind was going in 2 places there at once. And again, I'll say what they are. 1 mole into 3 moles H2 but only 2 moles of products, which are gases. Okay, therefore, an increase in pressure would favour the forward reaction, increasing concentration of NH3. I'd be pretty happy with that if I read that as an answer. Okay, so basically I'm saying the rules basically that an increase in pressure favours the side with fewer gas molecules. It'll only affect equilibrium which have gas molecules in them. I've said why it hasn't affected the first one, even though it's got gases in it. And in the second one I've said not only that it's affected it, but how it's affected it. Right, the next question. This is linking more to what we've just covered about Kc. Now if we see here, the Kc values are decreasing due to an increase in temperature. That's the relationship, so I need to say that. So an increase in temperature results in a decrease in Kc. This means, now this is the key thing for justifying, you need to say what that actually means. If this value is decreasing, this means the concentration of the products is decreasing as temperature increases. The reverse reactions being favoured. And we've already done this one in class, so we actually know that this is an exothermic reaction as well, but I'm going to need to justify it. An increase in temperature would favour the endothermic reaction as the equilibrium absorbs some of the extra heat energy. I'm going to chuck in the Le Chatelier's principle as my reasoning. Alright, this means that the reverse reaction is endothermic, so the forward reaction must be exothermic. Right, this question here is more about your thinking than how well discussed your answer is. It's a justification, just give the reasons, but because you have to think it through, that's why it's going to be worth a contribution towards excellence. There's still one more part of this question, and it's a calculation. Now, this is going to be a bit hard for me to show all of this on here. But really this is going back to what is the Kc for this reaction. So bear with me, this is not going to look pretty, but Kc equals the concentration of HI squared over the concentration of H2 times the concentration of I2. And as I say, I'm sorry, it looks a bit messy with working in Word, but that's all there is to it. The squared is because of the 2 in front of the HI here. All right, now they've given us some of these values. They want us to calculate the concentration of HI, which is the thing we've squared, at 941 degrees Celsius, given these other values. They've also given us that the Kc value is 46.8. So, 46.8 equals some unknown squared. I'm going to call it x because that's what my maths teacher always told me unknowns are. So I'm going to do it. Over 0.0190 times 0.210. Now to rearrange that for x to be the x squared, it'll actually be, but for x to be the subject, x squared equals 46.8 times 0.0190 times 0.210. And luckily I've got my calculator set up here, so 46.8 times 0.0190 times 0.210 equals, so 186,732, x equals 6732. Just double check I transposed that correctly. Yep. So, sorry, that's x squared. So therefore, the concentration of HI is going to be the square root of that. Which is 0.432 moles per litre. Now, I'm not going to worry about these other numbers. Everything was given to me to 3 significant figures, so that's what I'll stick to. 0.432 moles per litre, or moles per cubic decimetre if you want to call it that. And there we go, we have done an entire question as well to prove our understanding of equilibrium and equilibrium constant.